According to Newton's cooling law, two warm bodies in a continuous stream of air, if nature and area of their surfaces and the excess temperature are all identical, then their rates of heat loss also will be equal. So if we take two objects with identical surfaces and with the same excess temperature, the rate of heat loss from both the objects should be equal. So this phenomenon can be expressed using this equation: dq by dt equals Ka theta minus theta s. dq by dt is the rate of heat loss from both objects. K is a constant that depends on the nature of the surface. Capital A is the surface area. Theta is the surface temperature. And theta s can be considered as the surrounding temperature. So theta minus theta s is the excess temperature. For the rate of heat loss, we can apply mc d theta by dt equation as well. Since this expression has symbol c, that is the specific heat capacity, we can apply this equation in two cases in order to find the unknown specific heat capacity. So what we are going to do is, first we are going to fill this calorimeter with water. Since we know the specific heat capacity of water, by using this equation, we can find the rate of heat loss. Then we are going to fill this calorimeter with the liquid. So in both cases, when there is water and when there is the liquid, the rate of heat loss should be the same. Then using that information and this equation, we can find the specific heat capacity of the liquid. So that is what we have to do in order to find the specific heat capacity of a liquid. Then let's consider step by step how to continue the experiment. First, let's consider the materials and apparatus required for the experiment. We need a calorimeter with polished outer surface, and it should contain the lid and a stirrer. Then we need the thermometer, which is calibrated from 0 to 100 centigrades, an electric fan, a stopwatch, and a triple beam balance. Then we need the sufficient amount of water and liquid. So this is the list of materials and apparatus required. So you have to arrange those as shown by this image. So this is the calorimeter with the lid, and it contains the stirrer and the thermometer. This whole thing is hanged by threads to this stand shown here. When we fill the calorimeter with liquid or water, that liquid level should be below 1 centimeter from the brim of the calorimeter. Then there's this electric fan. It should provide a continuous stream of air. The calorimeter surfaces are submitted to this continuous stream of air from the electric fan. So that will be the experimental setup for you to do this experiment. Then let's consider step by step how to proceed this experiment in order. First, you have to measure the mass of empty calorimeter with the styro. Let's say that measurement is N1. Then you have to fill the calorimeter with liquid to a level that is below 1 centimeter from the brim of the calorimeter. So, somewhere here. Then, after closing the calorimeter with the lid, you have to suspend the calorimeter by this stand. Note that the temperature of water should be about 70 centigrades. Then allow the calorimeter to cool due to this continuous stream of air from this electric fan. Then while stirring, you have to get the temperature readings at 30-second intervals till the temperature of water is about 40 centigrades. Those temperature readings will be useful to draw the cooling curve for water. So cooling curve is something like this. If we take theta, the temperature for the y-axis, and time for the x-axis, we can mark those coordinates for the temperature at 30-second intervals. Then we can draw this curve. So this curve represents the cooling curve for water in this case. Once you get the temperature measurements to draw the cooling curve, measure the mass of the calorimeter with water. Let's say that measurement is M2. So we know the mass of calorimeter with water and the mass of the empty calorimeter with styro. So if we subtract M2 and M1, we can find the mass of water. That is M2 minus M1. Okay, now we know the mass of water, that is M2 minus M1, and the temperature measurements to draw the cooling curve for water. Okay, then we need temperature measurements in order to get the cooling curve for the liquid. For that, you have to remove the water from this calorimeter and wipe it well. Then fill the calorimeter with the liquid to the same level as water. So the volume of water we used and the volume of liquid we are going to use, both are same. Now the procedure is same as before. Take temperature measurements at 30-second intervals in order to draw the cooling curve. Finally, measure the mass of the calorimeter with the liquid. Let's say that measurement is M3. So M1 is the mass of empty calorimeter with the styro. M3 is the mass of calorimeter with the liquid. So if we subtract M1 from M3, you can get the mass of liquid. So now we have all the measurements required to find the mass of water we used and the mass of the liquid. Then we obtained the temperature measurements of water and liquid at 30 seconds intervals. Using the temperature measurements, we can draw the cooling curves for water and the liquid. So here the red curve is the cooling curve for liquid, and this black curve is a cooling curve for water. Then I need to remind you this equation. dq by dt, that is the rate of heat loss, is equal to Ka theta minus theta s. This also is equal to mc d theta by dt. So dq by dt is the rate of heat loss from the calorimeter. This K is a constant that depends on the nature of the calorimeter. So when there is water and when there is liquid, we maintain the surface nature of the calorimeter same. So K is same in both cases. Capital A, that is the surface area of the calorimeter, in both cases, that also is same. Then we have theta s, that is the temperature of the surrounding. We can assume the temperature of surrounding also did not change. So K constant, theta constant, A constant, then theta s as well is constant. In both cases, they didn't change. But the temperature of liquid and for water, it always keep changing. So we will have to consider the mean temperature of liquid and the water. So in order to get the loss of heat rate to be equal, we have to get the mean temperature for both liquid and the water to be same. So this value also should be same, that is mean temperature. For that, we are going to use the same range for both water and liquid. So this is the same range of temperature. So that is from theta 2 to theta 1. So if we calculate the mean temperature, the value is theta 1 plus theta 2 divided by 2. The value could somewhere be here. Theta 1 plus theta 2 over 2. Then this value also is the same in both cases. Both cases means when there is water and when there is liquid. So as you can see, for both cases, Ka, theta m, theta s are the same. So we can conclude that the rate of heat loss is same for both cases. Then we can write expressions using this equation and equate them. First, let's write an expression for rate of heat loss from water using this equation. So this is simple M. So the water, simple M should be the mass of water. So we have the mass of empty calorimeter, and this is mass of calorimeter with water. So mass of water should be M2 minus M1. Then multiply that by the specific heat capacity of water. Also, we have to consider the mass of calorimeter and the style. So that measurement is M1, and also that can be multiplied by the specific heat capacity of calorimeter materials. And if we add them at both values, this is this heat capacity of calorimeter and water. So that is the MC term. D theta is the temperature difference. So that difference is from theta 1 to theta 2. Then divide it by the time measurement. So for water, temperature drops from theta 2 to theta 1 to theta 2. This is the range. So the time required can be taken from this. So the temperature drops from theta 1 to theta 2. Time is from this value to here. So we can get that from this graph. That is TW. So we have an expression for rate of heat loss when there is water inside the calorimeter. Then let's write an expression to get the rate of heat loss from the liquid. So same as before, we have to include the heat capacity of calorimeter with the stirrer. So mass of calorimeter with the stirrer and the specific heat capacity of calorimeter material. Then for that we have had the mass of the liquid. Mass of the liquid should be M3 minus M1. M3 is mass of calorimeter with the liquid, which is the mass of empty calorimeter. So if we subtract those two values, we can get the mass of the liquid, that is M3 minus M1. Let's say the specific heat capacity of the liquid is simple C. So this is the MC term. For this one as well, the temperature range we consider is from theta 1 to theta 2. Here, theta 1, theta 2. So within that temperature range, as you can see, for the liquid, it takes a time period of theta L. So this red line shows the cooling curve of the liquid. According to that, the temperature drops from theta 1 to theta 2. So within that temperature drop, the time required is this much. So that is theta L. We can get that value from this graph here and divide to get the rate. divide this by that time period. So there is a theta L. So in this case, we noticed that the rate of heat loss in these both cases, when there is water and when there is liquid, are same. So these two expressions should be same. I'm going to put a equal sign here. So these two values are same. And all these terms are known except for the term C. C is the specific heat capacity of the liquid. So easily we can calculate a value for the specific heat capacity of the liquid, that is simple C.